What up, everyone? This is LeetCode 543, diameter of binary tree. Given the root of a binary tree, return the length of the diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in the tree. This path may or may not pass through the root. This is actually a little bit of a hint, and I'll get into that in a little bit. The length of a path between two nodes is represented by the number of edges between them. For example, this path 425 is the length of the path is 2, right? Because they would have two edges, 1, 2, right? And again, the edges are what connects nodes. Anyways, back to this part here. This path may or may not pass through the root. What this is telling you is that your path, let's say this tree might look a little bit different. The longest path may go like this, right? Right? It may not include the root node. So if you start from top to bottom in your approach, meaning let's check the path from maybe 1 all the way down to the left, or 1 all the way down to the left and then right. When you're doing this, right? Assuming our longest path is somewhere in this left subtree, now when we check the path here, we might get an answer, right? Our longest path is whatever, some number. Now when we move to this left subtree and we check the longest path again, we might actually find an even longer path than what we currently have seen so far. Okay, so the longest path may actually be something over here, right? But not including this root node. But this longest path we might look at paths. We might look at some in our longest path. We may look at certain paths that we already have looked at, right? When we checked up here, starting at the root node. So we're doing, repeated work. And so we don't want to have repeated work, right? We want to reduce overhead, because otherwise, as the tree grows, right, if we're re-looking at paths and stuff, because we're working top down, as our tree grows, our time complexity is going to get really ugly, right? Right, if we have like an n squared solution or whatever, in terms of time complexity. So how do we solve this? Okay, we're gonna actually work bottom up. Okay, and for me personally, this part here gives you a little bit of a hint, and it's telling you be careful working top down, right? Because your longest path may not pass through the root. Okay, so how are we gonna work bottom up? This solution that we're gonna get into is very similar to the solution for a LeetCode problem called balanced binary tree, where essentially you have to, it's very similar. The problem isn't the same, but the approach is very similar, where you're working bottom up to check if a tree is the left and the right subtrees are balanced in terms of they differ by no more than 1. Anyways, this isn't that problem, but I have a video on that problem, so go check it out. So it might help you understand our solution here a little bit more easily. So what we're going to do is we're going to go all the way down to the left. When we reach a node that has no child nodes, right, we're just going to return 0, right? We're at this 4, go to the left. There exists no node on the left child for 4, so we return 0. Then when we hit this 4, we go to the right. Okay, no child node, so we return 0. Okay, now when we're at this 4, we're gonna return the left plus the right, right? And we're gonna see, is that path the max diameter, or is it greater than the max diameter we have now or not? And if it is, we're going to set that as a new max diameter. Now, for example, in this 4, though, the max diameter is still 0, right? Because it has no child nodes. And then when we go up, we're going to add 1 plus the max of the left and the right subtree that we've checked so far. This may not make sense to you right now, right? But let's go through this example. So 2. Again, we added 1, right? So for 2, we know that the left subtree has a height of 1 so far. Okay, now let's go to the right. Again, 5 has no child nodes, so 0, 0, right? No, we haven't seen any diameter so far, so the max of what we've seen so far is also 0, right? Because there's no child nodes. So we add 1 because we're going up in the tree. Okay, now we're at 2. Okay. Now let's add the left and the right subtrees, okay? So this is 1 and this is 1, right? Okay, that would be 2. And so our new max diameter is going to be greater than what it currently is, which is initially 0, right? So the max diameter so far that we've seen is 2, right? Which makes sense because 4 to 5, for example, right? This would be a path of 2, right? So that's why our max diameter gets set to 2. Okay. Now we're going to go up and add 1, but remember, we're not just adding 1 when we go up. We're taking the max of the left and the right subtree and adding 1, right? Well, these are both 1, right? We can only go 1 to the left or 1 to the right, doesn't matter. So we add the max of the left and right, which is just going to be 1, and we add 1 plus that max. So 1 plus the max of what? Left and right here, which is just 1, so 1 plus 1. Okay, so we have 2 when we go up to this root node, which is 1. Okay, now we go to the right, and we're going to say, okay, no child nodes, right? So these, when these return up, they just return 0, right? Because, again, no child nodes for 3. Okay, now when we go up, right? When we go up, we're gonna add the left and the right subchild of 3, which is just gonna be 0 because it has no subchilds. And when we add the left and the right here, is that number greater than the max diameter we've seen so far? Right? 0 and 0, 0 plus 0? Well, no, so it doesn't matter, right? So our max diameter is still the same thus far. But when we return up, we're going to add 1 to the height plus the max of the left and the right that we've seen so far, which is 0. So we're just adding 1, right, when we go up to this 1. Okay? So remember, up here, we have a 2. At this 1, the left subtree has a 2, and the right subtree has a 1. Okay? Now we're going to calculate the max diameter so far. So we're going to take the left, which is 2, plus 1, right? It's just 3. Okay? 3 is 3 greater than the current max diameter? Current max diameter so far is 2, right? This path 4, 2, 5. Yes. 3, right? 2 plus 1, 3. 3 is greater than 2, so our new max diameter now is 3, right? Which would make sense because 4, 2, 1, 3. That's the longest path we've seen so far, which would be 3. So it makes sense that our max diameter gets set to 3, right? Additionally, we're not actually returning anything now, right? Because 1 is our root node. So when we go, we have nowhere else to go, okay? So we're done with the algorithm, and we just return the max diameter we've seen so far, which is 3, okay? So this is an O of n squared solution because we're going to visit every node, right? But we're just calculating the diameter as we work our way up, right? So let's say our max, this tree looked a little bit different. Our max diameter was somewhere over here, right? We would still go up to the root node and look over here and over to the left. But if the max diameter isn't at this root node isn't greater than whatever it is when we checked over here, then it wouldn't matter, right? Because we're returning the max anyways, which would be whatever the number is over here that we've seen so far. If that's the longest path is somewhere over here, right? And I hope me working through this example sort of makes sense. And again, I have another problem I've done called balance binary tree. It also has a similar approach, so I recommend that video also. It's kind of a good problem because it helps you visualize what we're doing because it has a similar approach. The problem statement is different, but the approach is similar. Okay, so we're gonna say max diameter, right? And this is just the mutable object, right? global variable. Yeah, so it'll work fine in the DFS function. Okay, so let's create a DFS function and pass it the root. Right, that's where we're gonna start. Well, we're not actually gonna start from the root. We're gonna recursively work our way all the way down to the left. We're starting down here, but we pass the root into this function, right? So we're gonna say if root is none, you return 0, right? For example, when we're at this 4 and we go to the left or to the right, we want to return 0, right? Because, I mean, there's no child nodes, okay? Now let's work our way all the way down to the bottom before we actually do anything. So we're going to say dfs root.left, dfs root.right, okay? Now we're going to say left is equal to dfs root.left, right is... And we need these variables, right? Because when we go up to this 2, we need to know what the height is from the left and the right. Because again, we have to add them, right? For calculating the max diameter. Okay? So we're gonna say max diameter of 0 is the max of the max diameter 0, right? Our global variable. Left plus right. Okay? Now we're gonna return 1. Oh, that's where we calculate the max diameter. And if we have to work our way up the tree still, we're gonna return 1 plus the max of the left and the right. Okay. Now we're gonna do dfs.root because that's our starting point, and we have to return the max diameter that we've seen so far. Checking that I spelled my variable names right. Okay. So again, remember what I was saying with our example, right? We're gonna go up and add 1 plus the... Again, when we're at this 4, the left and the right are 0. So left plus right is 0 plus 0. What is the max of the max diameter plus and 0 plus 0? Well, max diameter initially is nothing, right? So when we're at the 4, this doesn't actually get set to anything. Well, it would get set to 0, I think, because yeah. But it gets set to 0, which would make sense, right? Because at 4, our max diameter is 0. And again, because the diameter is the longest path, right? There is no longest path from 4, right? So now we go up. We take the max of the left and the right, which is 0, and we add 1 to it when we go up. So this 2, the left subtree has a height of 1. Now we go to the right. Again, nothing to check the max diameter here, right? Because 5 has no child nodes. So we go up, we add 1 plus the max of the left and the right, right? This 5 has no left and right, so it's 1 plus 0. Okay, so this is 1. Now we're at this 2, we check the left and the right. We add the left and the right, which is 1 and 1. That would be 2. What is the max between max diameter and 2? Well, our max diameter is 0 currently, so 2 would be the new max diameter, right? Which makes sense, because again, 4 to 5 or 5 to 4. That's the longest path so far. Okay, now we're going to go up. We're going to add 1 plus the max of the left and the right. Well, the max of the left and the right at this 2, it's 1 in either case, right? So 1 plus 1 would be 2, okay? For this, so at this 1, the left subtree, the height is 1 so far. The longest path so far for the left subtree at this 1 is 2. So we go to the 3. This 3 has no child nodes, right? So left plus right is 0 plus 0. Is 0 plus 0 a bigger number than the max diameter of 2 so far? No, it's not. So max diameter stays the same. We take, what's the max of the left and the right? Well, it's 0. So 0 plus 1 when we go up. It's 0, and then when we go up, we add 1, right? When we're returning. Okay, so 2 and 1. Now with this 1, check left plus right, which would be 2 plus 1. Is 3 greater than the max diameter so far? Yes, it is, right? Because the max diameter so far is this path right here, 4, 2, 5, which is 2. However, left plus right, which is 2 plus 1, that is 3. So our max diameter is 3. again, that would make sense because 4, 2, 1, 3, or 3, 1, 2, 4, or 3, 1, 2, 5, whatever path you use, right? That would be the longest path. So it would make sense that at this one, the max diameter would get changed, okay? And again, we're not returning anything else because we can't go up any further in the tree. So we exit the recursive function and we return the max diameter, which in this case would be 3, just like we expected, right? I hope this problem makes sense. I know this video might be a little bit long because I went really slowly through the examples, but I just wanted to make sure you understood the solution. I think there's a lot of videos on this particular problem, but not a lot of them kind of go super in depth with what the solution is doing. So I hope this helped. And again, I have another video called that I've done called Balanced Binary Tree, where we also work bottom up, and we calculate the heights to check if the binary tree is balanced. So I'll link that in the description if you want to go over it, because it's a very similar problem in terms of how you approach it, where you work bottom up. So anyways, I hope this video helped you, and I'll see you in the next one.